Okay, ever wonder what makes your phone screen so incredibly responsive? Or how your tools are so durable? Or, get this, what actually keeps your potato chips fresh? Well, the answer to all of those is a single technology that you've probably never even heard of, but it is everywhere. It's called sputtering, and it's how we build our modern world, literally one atom at a time. All right, so here's the plan for this explainer. First, we're going to pull back the curtain on what this invisible tech actually is. Then we'll dive into how it all works. I've got a really cool analogy for you. After that, we'll look at how it's evolved, discover where it's hiding in plain sight all around us, and finally, we'll explore what this incredible atom-thin precision really means for the future. Sound good? Let's get into it. First up, an invisible essential technology. We're going to uncover the science hiding behind everyday objects. So let's start with a bit of a riddle. What on earth could possibly connect a humble potato chip bag to a super high-tech aerospace component? I mean, at first glance, you'd say absolutely nothing, right? One's for your lunch, the other's for, a jet engine. But believe it or not, they share a fundamental high-tech secret. And here it is. The connection is an invisibly thin, perfectly applied layer of material. See, both of them rely on this ultra-thin coating, put on with just incredible precision to give them special powers. For the chip bag, it's keeping it airtight and fresh. For the jet engine part, it's protecting it from insane heat. And this process, it's quietly become a cornerstone of, well, pretty much all modern manufacturing. Okay, so how in the world do we actually make these perfect atom-thin layers? The process itself sounds super complex, but honestly, the best way to wrap your head around it is to think of it like a game of cosmic billiards. Seriously. Okay, so let's get the official sciencey definition out of the way. Sputtering is a process where atoms are ejected from a solid target material by bombarding it with energetic ions. Okay, what does that actually mean? It means we're literally knocking atoms off of one thing so they can fly over and build a brand new layer on something else. And trust me, that billiards analogy is what makes this whole idea just click. Okay, so picture this. We're inside a vacuum chamber. Step one, we fire a charged particle. That's our cue ball, at super high speed. Step two, it smashes into a block of material that we want to use for our coating. That's our target. Step three, bam! When that cue ball hits, it sends atoms from the target scattering everywhere, just like a perfect break shot in pool. And step four, those scattered atoms fly across the chamber and land on a surface, say a microchip or a piece of glass, and they build up atom by atom by atom into this perfect, super uniform, ultra-thin film. It's atomic billiards. Right, so this basic idea of atomic billiards has actually been around for a while. But of course, the story doesn't stop there. Over the years, scientists and engineers have come up with some incredible upgrades to the sputtering toolkit, making the whole process faster, way more efficient, and a whole lot more versatile. So in the early days, you had your basic direct current, or DC sputtering. It was the foundation. Then came a massive leap in efficiency with magnetron sputtering, which cleverly uses magnetic fields to trap electrons and really speed things up. But the real versatility upgrade, the one that blew the doors wide open, was radio frequency, or RF sputtering. And today, we have advanced methods like co-sputtering that let us create these incredibly complex, multi-element films. It's been quite an evolution. So you might be asking, why was that RF upgrade such a big deal? Well, here's the thing. The early DC sputtering could only work with materials that conduct electricity, like metals. That was a huge limitation. The problem was, a positive charge would build up on insulating materials and just stop the whole process. RF sputtering brilliantly solves this by using an alternating current. And just like that, we could suddenly coat insulators like ceramics and plastics. It was a total game changer. So this table kind of lays it all out pretty clearly, right? You've got DC sputtering, the foundational, simple one for conductors. Then you've got magnetron sputtering, the high-speed version, also for conductors, that uses that cool magnetic confinement. And then you have RF sputtering, the real workhorse of the group, which can coat all materials. Each one is a different tool in the toolbox, perfect for a different job. All right, we've covered the what and the how. Now for, in my opinion, the coolest part, the where. This is where this invisible technology suddenly becomes very, very visible in our everyday lives. So where is this atomic scale process actually happening? I think the answer is going to surprise you. In fact, you're probably holding it right now. No, I'm serious. Your smartphone, your laptop, your TV, they are absolute masterpieces of sputtering technology. Every single tiny pixel on your screen is controlled by something called a thin film transistor, or TFT. And guess how those are made? Yep, sputtering. Those super crisp, high-performance displays, they use sputtered films of a cool material called indium gallium zinc oxide, IGZO for short, which gives them that incredible clarity and battery efficiency. This tech isn't just helpful, it's absolutely essential for the electronics we can't live without. But it's not just about our gadgets, not by a long shot. These films are also workhorses in heavy industry. They provide that critical wear and corrosion resistance that's vital to things like industrial tools and aerospace components. We're talking about parts that have to withstand absolutely incredible stress without failing. And really, the applications just keep expanding. Sputtering is what creates the crucial layers inside solar cells that turn sunlight into electricity. It's used to apply antibacterial films on biomedical implants, making them safer inside the human body. It's the secret behind the ultra-hard protective coatings on cutting tools and drill bits. It really is the hidden giant of modern technology. So if sputtering is already doing all of this incredible stuff, you have to wonder, what's next? Well, the future is all about taking this amazing atomic level control and refining it even further to solve even bigger problems. Just take a look at the kind of performance jump we're talking about. This chart shows sputtering's effect on those thin film transistors we mentioned. Now, electrical mobility is just a fancy way of saying how fast electrons can zip through a material. And as you can see, when we use advanced sputtering to create that IGZO film, the improvement over a conventional film is just huge. And what does that mean for you and me? It means faster, more efficient, and more powerful electronics. And this really gets to the heart of the matter. Sputtering has evolved beyond just being a coding technique. It's now a true design tool. It gives us this unbelievably precise atomic level control to actually engineer the materials of tomorrow, creating substances with brand new properties that just weren't possible before. So, that leaves us with one last, pretty fascinating question to think about. Now that we can literally build materials one atom at a time, what problems are we going to solve next? More efficient solar panels, revolutionary medical devices, maybe even materials that we can't even imagine yet. The future isn't just something that's coming, we're actually building it, one single atom at a time.